Hi, I'm Summer and I'll be your interviewer today. I work here at Minmer headquarters on the Frog team, and today you'll have 45 minutes to do your coding interview with 5 minutes for asking questions. So, would you like to ask the questions now or at the end?
At the end, please. I definitely want to ask questions about the frog team, but no, let's do the code first.
Okay, cool. Let me go ahead and paste this. So the first question is going to be, given a string, return true if it forms a palindrome. Additionally, uppercase letters can be treated as lowercase letters, and only alphanumeric characters can contribute to a palindrome.
Okay, great. I do have some clarifying questions about the requirements. So, number one, can we be given an empty string?
No.
No. Okay. What's the longest length that the string can be?
Just a very large number.
Large number. Got it. Okay. And to clarify, it's only letters and digits that count towards a palindrome.
Yep.
Okay, gotcha. So it's a miscellaneous character, like outside of those, we ignore it. Okay, cool. Is there any white space?
Yeah, you can be given white space.
Okay, so and I assume that's, apart from the alphanumeric characters, you can get miscellaneous, just about anything. Last question. So uppercase characters, it says it's treated as lowercase characters. Is that correct?
Yep.
Okay, cool. Just sounds like a conversion of some sort. All right, so the brute force, and I open up the drawing mode. Okay, so if we had something like a classical race car, maybe a dollar sign in the middle, obviously this is a palindrome. The brute force could be to just make a big O n pass over this and add alphanumeric content into a string. This is called temporary for short, sure. Um, and we'd add race car and ignore the only invalid character. When you have temp, then you can just do a literal reversal of it. In this case, to get the same exact string, it's a palindrome, race car. You can then compare the two, see if they equal. In this case, they totally do, and return false. Not false, true, sorry. So in retrospect, you have one big O n. You do have another big O n as well to do the actual reversal. For the time complexity, the space complexity is sadly also big O n because of this temporary string that takes up as much space as the original input string. Okay, that's okay, but can I do better? Probably. Okay, so I think the intuition for me is, palindromes are read the same forward as they are backwards, obviously. And I can kind of simulate that and mimic that, mime that with two pointers, one at the beginning, one at the end, and just work our way inwards. I'm not sure what to do with miscellaneous characters, but let's see. I'm going to scroll down just a little bit in the drawing mode. So let's say we had something like uppercase R, randomly two underscores. So digits do count towards a palindrome, like I clarified. Maybe after that, you have like a lowercase r or maybe a at symbol first. Okay, so this is a palindrome, but if I have two pointers left and right, which makes sense in my head, we can compare R and R, but hold on, this is uppercase where the left pointer points to. We can convert it to a lowercase character, so that's going to be somewhere in our code. Then you can compare R and R, which are the same. So we have a palindrome so far. We can increment left, decrement right. Cool. Now for the left pointer, we do it all over again, but we want to skip all the miscellaneous characters. Okay, so why not a nested while loop in the overall loop, which I will argue overall will still be a big O n solution, but we can skip this underscore because it's not alphanumeric. Left gets incremented where it will be incremented yet again because underscores don't count to a one where that does count, so we can stop there. So inversely, we can give the same treatment to this right pointer. An asterisk symbol or an at symbol is not valid, so we decrement R, and then our nested while loop stops because one counts. Then you can do that repeated logic where I guess by the instruction of the code, you'd convert one to a lowercase one, which just is just one. So then you compare, does one equal one? Yes, it does. you increment L, decrement R. Okay, so this, for the outer loop, you can terminate that because the base case is if the left and right pointers are on the same character, or I can foresee a case where they both pass each other as well. If you have like an even number of characters, then you've exhausted every single character and you return true. You have a valid palindrome. That makes a lot of sense to me. So yeah, the overall time complexity is still a single big O(n). You only process each character, one time, but the space complexity is greatly reduced to constant space because you only use 2 pointers left and right to work inwards. So I do like that approach a lot better. Can I try to translate that into code?
Yes, please.
Cool. All right. So let's call it something like is palindrome. That makes a lot of sense to me. It takes in a string. I'm going to call it S. Here's a type hint. And then it's going to return a Boolean of whether or not it is a palindrome or not. So first things first, we need our left and right pointers, LR for short. It's going to equal to the 0th index. And also the last index, -1. Now I know that we're going to have a while loop, an outer while loop that will work its way inwards. But if you ever make it out of that, then we return true. You have a palindrome. You've exhausted every single character. Great. But if not, let's go into the main bulk of the logic where as long as the left pointer is lower than the right pointer, you're going to be checking for a palindrome. So we're going to have a nested while loop for the left pointer that so long as the character there is not alphanumeric, then we can add 1 to the left pointer. And I'm going to do something terrible. Copy and paste for the right pointer. But here's the dangerous part. We're going to have the opposite logic where you're going to decrement the right pointer instead. That makes sense to me. So after that, if you get to, both of them get to the 1 in the example, then you can compare the two. That if they're not equal, then you immediately return false. You don't have a palindrome, but we want to make sure this is where you're going to convert both of them to lowercase, which if it's like a 1, it'll still be a 1. That's okay. After this, if they do equal, you want to progress your while loop along, add 1 to L, -1 to R. So that seems correct to me. Awesome. I'm done.
Do you want to try any more test cases?
No, I think this implementation should cover everything. I kind of did a dry run unofficially as well. So
What if you had a string that only had 3 underscores?
Okay, so that's a good test case to verify, because I should. So you're saying if we had 3 underscores, I just drew that out. Then going through the code, line 21, you'd initialize both pointers and then enter the while loop that so long as they don't cross, you're going to have a nested while loop on line 24 for the left pointer, in which case you're going to keep incrementing it on line 25 because it's not alphanumeric. Once again, not alphanumeric. And then now I see the issue. You increment it again. It's out of bounds. The code would it would blow up because you're accessing an element that's not part of the array. Okay, cool. So I still want to retain the ability for the left and right pointers to go inwards and skip miscellaneous characters, but not past the other pointer. Right. Okay, so for the left pointer, what we can do is keep the conditional on line 24, but also make sure it doesn't pass the right pointer. And so in that case, it would land on index 012 on index 2. The right pointer on line 26 then would not move at all because you don't want it to pass the left pointer. Okay, and then you move on with the code as normal. You compare technically an underscore with itself, which is fine. You don't return false. And then you decrement R on line 33 and then left added 1 on line 32. They've crossed, so our while loop stops and we return true, which that does make sense to me because if you ignore miscellaneous characters in this string, you just have a empty string. That's technically a palindrome. That makes sense to me. Okay, so let's make that change. So on line 24, you don't want both pointers to cross, and same thing on line 26 for the right pointer. Okay, so that makes sense to me now. There we go.
Nice. Does that change your space or time complexity?
Good question. So the time complexity, I'm going to write it out. It's going to still be big O N, a single big O N, and then space complexity will be constant space still because we only use the 2 pointers. Yeah, it doesn't change.
All right, that looks really good. Let's go ahead and move on to the next problem. All right, pasting that. So given an array of integers and a target integer, determine if it has a subarray of integers that add up to exactly the target. And you can see there's an example there.
Okay, cool. So I have a bunch of questions. So to be clear, we're given a list of integers as input. Is that correct?
Yep.
Okay. Can we be given an empty list as input?
Yes.
All right. So in that case, we return false because you literally can't find any numbers physically to add up to any target. Okay. Can we be given negative numbers?
No.
No. Okay. What about zeros?
No.
So on that note, the target can only be positive. Is that right?
That's correct.
Okay. And last question. So what is the upper bound length of our list?
A large number.
Large number. Okay. Okay. That makes sense to me. So as far as potential solutions go, my immediate thought is to just do a nested loop to look at every single possible subarray. So I'm going to scroll down yet again in the drawing mode, and I'm going to draw out this input. So 4, 2, 5, 2, 6, 1 with a target of 9. Okay. So again, we can try every possibility. I can just have an I pointer there at the very beginning to go towards all the elements. And then you have a nested loop spearheaded by pointer J that starts at I. And then from there, you can also go through all the elements, adding each and every one to a sum variable. And then if we ever get a target of 9 exactly, then we return true. That's our answer. So just going through this, you're going to have 4, you increment J, and then nest the for loop. You have 2, so you add that to 4 to get 6, not 2. Again, you have a 5, so you add that to 11, but that is greater than our target of 9. So we can break out of that loop, shift 1 along, and just honestly do it all over again. Sum is going to be reset. So you're going to add the 2 and then, with the pointer J, and then shift it to 5, where you add that to 2 to get 7. That's lower than our target. So we want to keep going. Increment J, where it points to a 2 now, you add the 2 to the 7 to get 9. And then, again, on every iteration, you do that check. Does the sum equal the target? And in this case, it totally does. So you break out and return true. That'd be your answer. However, the time complexity would be n squared because of the nested loop with I and j. Can we do better than that? Probably. Okay, so to think on this, I'm going to draw out the same example, 2, 6, 1. So we still have a target of 9. So this is kind of what I'm thinking. So if you have a pointer I, anytime you add a number to the sum that we'll still have, kind of like in the previous brute force solution, our sum would only ever go up, right? So on 4 here, you add it to the sum and it goes up. On the next iteration, you have a 2, you're only ever given positive numbers. So I'm very confident to say that the sum would only go up if you include numbers. So with a 2, we get a sum of 6. You move I to the next iteration where you have 5, add to the 6, it goes more positive to 11. And in the case where the sum is greater than our target, we need some sort of correction. So we can have a lagging pointer, a 2-pointer approach, kind of like we did in the very first problem, where you can exclude positive numbers, which inversely would, make our sum go down and kind of correct it towards our target of 9. So if this is kind of the Okay, if it's the window, which it's pretty clear now, we're going to use the sliding window technique. If this window includes 4, 2, and 5 for a sum that's too great, you're going to increment L to exclude the 4 to get this window to 5, which excluding the 4 gets us a sum of 7. That's lower, but we're on the right track to our target of 9. On the next iteration, which I will rename I to the right pointer, that makes sense. We have a 2. You can add that to a sum of 7 to get 9. And then again, on each iteration, check, does the sum equal the target? Yes, it does. We return true. Here's the window that equates to our target of 9. Okay, I like that a lot. And in the case where the right pointer exhausts every single element in the array and reaches the end, we'd oppositely return false because you just didn't find a valid subarray. The time complexity should be a lot better. It's a single big O n because you only did one single pass. And then the space complexity is big O 1 because you only use 2 pointers, kind of like the palindrome problem. So I actually like that quite a bit. Can I try to decipher this into code?
Yes.
Awesome. Okay, so let's call it has valid subarray. Sure. I'm gonna scroll up just a little bit. It's gonna take in a list. Let's call it nums. Why not? As well as let's have a type hint for it as well. It's gonna be list of ints, and then it's gonna take in a target. Let's just call it target. It's gonna be an integer, obviously, and I'll pass in nothing else, but I'll return a Boolean of whether or not we found that subarray or not. So first things first, let's have the left pointer initialized. We need a sum as well. And we're going to initialize the right pointer in the for loop. So for right in the entire list, you're going to go through the motions of a sliding window. But I know that outside this for loop, if you reach the end, if the right pointer exhausts every element, you'll return false. We never found one. But on each iteration of the sliding window, we'll do a bunch of things. So one, regardless, we'll add the number at the right pointer, into our sum. And we might have to do some self-correction in the case that the sum exceeds our target. So a while loop for that, because you might have to minus a lot of numbers. So if the sum is greater than target, so long as that's the case, we'll definitely add one to the left pointer. But at the same time, you have to exclude the pointer's value pointed by left there as well. So that's denoted by nums at left. We'll keep doing that. And once it's kind of corrected, then we make an if statement check. If the sum ever equals the target exactly, we return true, and that be the answer. So yeah, that looks right to me. Can I go through a dry run real quick to make sure that this works?
Yeah.
Okay, cool. So on the drawing mode, that's randomly say we have 1, 2, 3, 4, simple, with a target of say 12. Okay, so on line 54, you have the left pointer initialized. You have a sum variable as well, as always, initialized to 0. So you initialize a right pointer in the for loop for our window, in which case the first thing you do on line 57 is add 1 to the sum. So the window of that is just a singular element, which is 1 that's lower than our 12. So line 63 is not true. You move on to line 56 again, where the right pointer is incremented to a value of 2. Line 57 says we add 2 to the sum to get 3. We don't do any self-correction on line 59 because that conditional is not true. Line 63 says 3 is not 12. That's obvious. You do it all over again on line 56. You have a 3 now, which I can kind of foresee what's happening here. You add 3 to 3 to get 6, and you do it again with the 4 to get 10. And then you make it out of the whole list. So what happened here was every element added together could not reach our target of 12. So we return false in that case in line 66. Cool. So I think the code does work in that case as well. Awesome. But yeah, to finalize the time complexity, and I'll write that out, is big O n, where n would be the number of integers in the list. You got to go through each one. The space complexity is big O 1 since I only use fixed variables. The 2, I guess, with the sum as well. But yeah, that's what I got.
Okay, cool. For this next part, you don't have to code anything at all, just an explanation is fine. But how would your solution change if there were negative numbers?
Okay. If there were negative numbers, interesting. I'm going to scroll down a little bit here. So I do have a question. So does that imply that the target can be negative too?
Yep,
In zeros as well.
correct.
I see. And in the array. Gotcha. Okay. Um, interesting. So I'm not immediately sure, but I'm just going to write out an example. Maybe something like -1, there can be negatives, 2, 3, sure, -4 with a target of 5. I'm just eyeing this window right here. Okay. So to phrase this, how can we find whether there's a valid subarray in this array that equates 5? Obviously there is, we'd return true in this case, but I'm trying to see what math we can manipulate. So we know that this subarray is -1, this one's +1, this one right here would be 4. Okay, so if we do like 4 minus 5, the target of 5, this guy right here, we'd get -1. And essentially, if there exists a complement subarray that adds up to -1, which in this case we do, then we can return true. We have a valid subarray. So my thought is, if you know that this whole subarray here equals 4, and you know you want a subarray that sums up to a target of 5 right here, if you minus them, you'll get what's left over, this one right here. In this case, is just a single element. It can be multiple in a row. Then you have a valid subarray. So these are all trackable things. So what I can do is keep track of the sum, or technically the prefix sum, kind of like how we did in the previous problem, of the -1 first. So yeah, we'd have a single for loop and keep track of the prefix sum. So the next one would be +1. The next one would be 4, +4. And on each iteration, you would go, okay, what's the prefix sum you currently have? The +4 minus the target of 5 to get -1. Does that exist in this data structure? Which, speaking of which, would be a set, because you can look things up in big O1 pretty fast, to say, yes, I do have a -1. Okay, we return true, and that'd be your answer. I like that. But yeah, because the time complexity is only big O(n), and the space complexity would also be big O(n) because of our set here. And on that note, I do foresee an edge case where I feel like if you add up all these numbers, somewhat similar to the previous example, but not really, and you get, in this case, 0. If your target was, 0, because it can't be, then you minus the 2 to get 0. You're looking for a valid or a complement subarray of 0 that we'd never compute because it's a sum from the beginning. Okay, so in that case, we'd just but we'd insert a 0 manually into the set or something to find valid subarrays that start from the beginning and end at some point. But yeah, I actually really like that idea. I can definitely code that up as well.
No, it's okay. No coding is required. I got all the signals I needed. Do you have any questions for me with the time left over?
Yes, actually, yes. So I remember you mentioned a frog team. Do you actually work with frogs? Is it part of the AR VR wearables team? Because
Okay, here's the feedback that I would submit after Min's interview. So, the feedback suggests that the candidate displayed strong problem solving skills and ability to disambiguate the requirements, asking clarifying questions where necessary. Candidate also referred back to the established requirements to help guide their verification. However, it was noted that the candidate failed to identify a critical edge case in the first easy problem due to an oversight of an entirely non-alphanumeric string. When asked to try more test cases, they refused. After a suggestion to try out a certain test case, candidate complied and quickly figured out the bug. It was also noted that the candidate pushed to implement the second medium problem when initially told a verbal explanation was sufficient. This may be an indication that the candidate struggles to take feedback, and more resources must be involved to set the candidate on the right track. Finally, it was noted that this particular candidate demonstrated clear communication and solved both problems quickly. Feedback also indicated that the candidate wrote clean and concise code with reasonable justifications for variable names and overall decisions. Time and space complexities were correctly stated. Helpful whiteboarding was utilized to walk through explanations. When compared to other candidates, the decision was made to move forward with the candidate. Thanks for interviewing with us today. I hope that this was helpful. We really appreciate your guys' support.